Have you ever just looked around and wondered what makes everything, well, tick? From the massive dance of the planets all the way down to that frustrating moment your phone slips out of your hand? It turns out there's a set of rules for all of it, and that's physics. It's basically the instruction manual for the entire universe. And today, we're going to learn how to read it.
So think about this for a second. It's something you've seen a million times. If you just drop a ball, boom, straight down. But if you throw it, it makes that nice, graceful arc through the air. Why the difference? I mean, gravity is pulling on both of them, right? This simple little puzzle is right at the heart of what physics is all about. And by the end of this, you're going to know the secret.
Now, to get to that answer, we can't just dive into the deep end. We've got to build our understanding from the ground up. You see, physics has its own language, its own set of tools for looking at the world, and that's exactly where we're going to start. We're going to learn how to speak universe.
So here's our game plan. Our journey today is broken down into 4 key parts. First, we'll look at the physicist toolkit. How do we even talk about the physical world with any accuracy? Then we'll get into telling the story of motion, which is all about describing how things move. After that, we'll ask the big question, why do they move? That's all about the push and the pull. And finally, we'll tie it all together with the fuel that powers everything, the universe's currency, energy.
So let's get into part 1, the physicist's toolkit. Before we can describe a single thing, a planet, a car, a ball, we have to be able to measure it properly. This is the absolute bedrock of all science.
At its core, measurement is just about putting numbers to the things we see. But for those numbers to mean anything, they have to be both accurate and precise. Accuracy means you're getting the right value, like when you read a ruler. You have to look at it straight on, at eye level, so you don't get the wrong mark. That's called avoiding parallax error. And precision? That means if you do it again, you get the same result. A cool trick to boost precision is, say, timing 20 swings of a pendulum, and then just dividing that total time by 20. That little bit of math smooths out any tiny errors and gets you a super reliable time for just one swing.
Now, our measurements come in 2 basic flavors. The first one is a scalar. A scalar just tells you how much. That's it. Think of the speedometer in your car, it just says 50 miles per hour. The second flavor is a vector, and a vector tells you how much and which way. That's like your GPS, telling you you're going 50 miles per hour north. In physics, that extra little piece of information, the direction, is an absolute game changer. All right, on to section 2, telling the story of motion. Now that we have our toolkit, we know how to measure things, and we know about scalars and vectors, we can start describing one of the most fundamental things in the universe, how stuff moves.
And here is our first big test of that scalar versus vector idea. Speed is a scalar. It's just a number. Velocity, on the other hand, is a vector. It has that all-important direction. So imagine 2 cars. They're both going 50 miles per hour, but one is heading north and the other is heading south. They have the exact same speed, but totally different velocities. It's a crucial difference.
One of the best ways to see motion is with a graph. Seriously, think of it like a story. On this graph, time is always moving forward along the bottom axis, and how far you've gone is measured up the side. So what does a completely flat, horizontal line mean? Well, that's the boring part of the story. Time is passing by, but your distance isn't changing one bit. You're just stopped, standing still.
Okay, now the story gets more interesting. A straight line that's sloping upwards means you're on the move. You're covering distance as time goes on, and because the line is straight, you're doing it at a steady, constant speed. And what's really cool is you can see how fast you're going. The steeper that line is, the more distance you're covering in the same amount of time. In other words, you're going faster.
And the plot twist in our story? A curving line. If that line starts getting steeper and steeper, it means you're covering more and more ground with each second that passes. Your speed is increasing. You're hitting the gas pedal. You are accelerating. That curve is the visual signature of a change in motion.
So let's see how this plays out in the real world. Think about a skydiver. The second they jump out of the plane, the main thing acting on them is gravity, which is pulling them down and making them accelerate like crazy. But as they go faster and faster, air resistance, this upward push or drag, starts fighting back. And the faster they go, the harder the air pushes. Eventually, they get to a point where that upward push from the air perfectly balances the downward pull of gravity. The forces are in a truce, and at that moment, the acceleration stops, and the skydiver falls at a constant, very fast speed. We call that terminal velocity.
Okay, so we're getting pretty good at describing motion. But why does it change? What causes that acceleration curve on our graph? The answer is forces, the pushes and the pulls of the universe that are actually causing things to happen.
Now, before we go any further, we have got to clear something up that trips up a lot of people: the difference between mass and weight. Mass is just the amount of stuff an object is made of. It's measured in kilograms, and it's the same no matter where you are. Earth, the moon, deep space, doesn't matter. Weight, though, is the force of gravity pulling on all that stuff. It's measured in newtons, so your mass never changes, but you'd weigh a lot less on the moon because the moon's gravity is way weaker than Earth's.
This brings us to the legend himself, Sir Isaac Newton. His first law is sometimes called the law of inertia, but honestly, I like to think of it as the law of laziness. It basically says that things just want to keep doing whatever they're already doing. A book on a table, it's going to stay there. A satellite drifting through space, it's going to keep drifting in a straight line forever. The only thing that can change that is an unbalanced force, a push or a pull that isn't being canceled out by something else.
And this, well, this is the big one. Newton's second law, F equals m. It might just be the most powerful little equation in all of physics. It's just so elegant. It tells you everything you need to know about changing motion. Want something to accelerate more? Well, you can either push it harder, increase the force, or you can make it lighter, decrease the mass. That's it. It's the perfect link between cause, which is the force, and effect, which is the acceleration.
Another really key idea here is momentum. You can think of it as an object's quantity of motion, or its oomph. A huge freight train moving really slowly has a ton of momentum because its mass is enormous. But a tiny bullet moving incredibly fast also has a ton of momentum because its velocity is so high. And here's the really amazing part. In any collision, the total amount of momentum of all the objects before they hit is exactly equal to the total momentum right after. It's never lost, it's conserved.
Okay, this leads us to our final and maybe the most profound section of all. We know that forces make things happen, but what pays for it all? What's the fuel? The answer is energy. It's like the universal currency that makes every single interaction possible.
And man, energy comes in so many different forms. There's kinetic energy, which is the energy something has because it's moving. There's gravitational potential energy, which is stored up in an object you're holding up high. There's chemical energy packed into a battery, elastic energy in a stretched-out rubber band. The list goes on. But the key thing is, it's all the same fundamental stuff, just wearing different outfits.
And that brings us to what might be the single most important rule in all of physics. Seriously, energy cannot be created and it cannot be destroyed. The total amount of energy in the entire universe is fixed. It's constant. All we can ever do is change it from one form into another.
And a simple pendulum is the perfect way to see this in action. It's just a beautiful energy-swapping machine. So, at the very top of its swing, the bob stops for a split second. At that point, it has zero kinetic energy, but its gravitational potential energy is at a maximum. Then, as it swings down, that stored potential energy gets converted into kinetic energy, the energy of motion. Right at the bottom, it's moving its fastest, all kinetic, no potential. And then, as it swings up the other side, that kinetic energy gets turned right back into potential energy again. The energy just transforms back and forth, but the total amount is always the same.
So how do we connect the world of forces with the world of energy? We do it with a concept called work. Now, in physics, work isn't about your 9-to-5 job. Work is the official term for what happens when a force actually moves an object over a distance. It is, quite simply, the transfer of energy. When you throw a ball, the force from your arm does work on it, transferring chemical energy from your muscles into the ball's kinetic energy. Work is the transaction that allows the energy to move.
So let's go all the way back to that first question. Why does a thrown ball follow that curve? Well, now we know. The force from your hand does work, giving it kinetic energy that moves it forward. But at the exact same time, the constant force of gravity is pulling it down. And it's that perfect combination of moving forward while also falling down that creates that beautiful, predictable arc. Everything we've talked about today, vectors, forces, energy, it all comes together to describe that everyday magic. But what happens when we look at things that are really, really small, like an atom, or things that are moving incredibly fast, near the speed of light? Well, it turns out the rules start to bend a little, and that is a story for another time.